Let's begin with the information on this teacher's whiteboard. What does it tell us about multiplication? G'day, Doug Williams here. Welcome to this multiplication journey workshop. It's a bit like one of those videos promoting the holiday of a lifetime. You learn lots from it, but then you still have to do your research and plan your schedule when it's finished. First, let's dig a little deeper into the teacher's 3 rows of 7. We can also say 3 times 7 because there's 3 times that we make or draw or say 7 things. And we can use 3 cross 7 as a shorthand for saying or writing times or rows of. The total of the yellow plugs here is 21. And we can calculate that by partitioning the array and breaking the problem into smaller parts. As learners explore these arrays, we can expect them to keep some sort of journal. Why? Because a mathematician needs to keep a journal while they're exploring a problem. As you explored, you've probably already started to ask the mathematician's question. And the next question might be, you might need to pause the video to take a good look at this first example. The next 2 examples are the same, but different. Pause if you need to. Let's take a look at some learners using this array model. As part of a professional development program, teachers at Loxton North Primary School took a multiplication journey right across the school from junior primary to year 7.
Okay, so I set up an array and recorded it over here, and now I'm going to read it out to Steph. So 2 rows of 3 Yep. And then 2 rows of 1. Mm-hmm. 3 rows of 3. Yep. And 3 rows of 1. And that's it.
I've turned over my poly plugs and divided them in with my straws, and I've worked out the things. Yeah.
What are you going to do, Andrew?
I shall work out what Shannon's saying and turn it over my poly plugs so I had the exact same thing as what she had.
Okay, cool.
And 2 rows of 3.
Oops.
Yep. Plus 2 rows of 4.
Yep.
That's all.
You kind of need more than one straw for that.
You need 2 straws.
Oh, yeah.
Can you work out where you put your 3 rows of 3 wrong, Andrew? Could you put your 3 rows of 3 somewhere different?
And then straws go along there and along.
Read it again, Shannon.
2 rows of 3.
Yep.
2 rows of 4.
Yep.
3 rows of 3.
Oh, I get it. Yep.
And 3 rows of 4.
Yep.
Encouraging the use of journals during exploration makes it easy to build a bridge from making arrays to drawing arrays, and that sets us up for multiplication calculations in a different way. All multiplication of 2 numbers can be represented by a rectangle, and the straws can be placed anywhere on the rectangle to partition it into smaller parts that make calculation easier. But 2-digit numbers are already partitioned. They're partitioned into tens and ones, so it makes sense to use the partition that's there, and it happens to produce easier calculations. We don't really need the squares on the paper anyway after a bit of practice, so just sketching the rectangle and making a sort of table format does the job quite well. After a bit more practice, if you're working like a mathematician, it's pretty natural to ask the backwards questions. Algebra goes back to the fork in the road where we decided that the tens ones partition was a good one to use, and it was, because it does help us do calculations when we know the numbers. But algebra says, what about all those other places we could have placed the straw to make the partition? And it looks at the possibilities that can happen there. And what happens is everything stays the same. The multiplication of two numbers is still represented by a rectangle. The straw can be placed anywhere, and in doing so it creates two parts of the one number. We still have A rows of B and A rows of C, and the sum of the parts is still the whole. So it doesn't matter what single-digit number or what two-digit number is used, and it doesn't matter how the two-digit number is split, it always works out the same way. So mathematicians have called this a law called the distributive law, and they have found a short way to write it by agreeing that if a letter stands next to a bracket, or if two letters are standing next to each other, it means that they should be multiplied. If two numbers are involved that are both two digits, then everything still stays the same. The top section of the diagram operates as we just saw, and so does the bottom. But this time, four parts are combined to make the whole. This is just a double application of the distributive law. The grey line represents that double application, and I've just put it in to remind you of where the four parts come from. Looking at special cases can sometimes provide an interesting adventure, and in this case, a square is a special case of a rectangle. So this special case of expanding brackets has produced another little useful algebraic rule, which in itself turns out to be a special case of a bigger picture called the binomial theorem, which is tackled in the senior school. Now, apart from a couple of evaluation questions I invite you to include in your session, and some references to other things that might stimulate your multiplication journey, we're done. Go forth and multiply. See ya.